You observe some data for which you create a bar chart. You see the data is normally distributed, but there are some outliers. So you want to use a robust estimate by encoding prior knowledge. The corresponding directed graphical model consists of the observations, for which we have n, and latent parameters of the normal with their according hyperparameters. We want to use variational inference to infer the posterior on the two parameters. So in total, we want to use variational inference by mean field approach for the normal with unknown mean and unknown precision. Hi, welcome to this new video. As said in the intro, we want to use variational inference by the mean field approach in order to find the posterior over the latent mu and tau for the precision of some normally distributed data. And this directed graphical model is derived from our idea where we found the true posterior. So you might ask yourself, well, if there's a true posterior available, what is the purpose of using variational inference? But I find it a good application scenario for the mean field approach in order to see it in action. And we can then use the true posterior to compare our surrogate posterior we find by variational inference to the true posterior. And for reference, let us note this down that the posterior, which is the probability over mu and tau given the data, which essentially is the observations that we made or that you can see in the bar chart here, is indeed tractable, or at least here it is tractable, in our case for the normal distribution, but assume it wasn't, which we will be doing for the next derivations in order to find our update equations. Let us also note down the different distributions that we encounter in our directed graphical model. And if this graphical model sounds strange to you, I would advise you to watch the video on the true posterior derivations where I come up with this. And essentially what you see here, this relation also between the tau and the mu, is a Gauss-Gamma or a normal gamma distribution. And of course this then consists of the following distributions, so that a tau is distributed according to the gamma over tau under the parameters alpha 0 and beta 0. These are our hyperparameters. Mu is distributed according to a normal over mu under the hyperparameters mu 0 and tau times tau 0 in brackets inverse. Our tau 0 in essence is a precision multiplier. And then we have our xi, which is the data that we observe, where we think it is normally distributed over xi under the latent mu and tau inverse, and of course I always use the inverse here because this is mimicking the variance. Then let's note down the idea for the variational inference, that we want a surrogate posterior, and the surrogate posterior is a q over tau and mu that is approximately, or that is close to our true mu and tau, or maybe the order is the other way around, however you like it, given the data. And recall in earlier videos we derived that for this we have to minimize the KL divergence between the two, which is equivalent to maximizing the elbow. In the last video we then used the mean field approach in order to find a specific set of families that can be used in order to find surrogates. And this mean field approach was given in the idea that we create independent distributions that are just multiplied with each other. So the mean field approach, which is that our q over mu and tau is given as a q of mu times a q of tau. Of course, so far we don't know the functional form of this mu and tau distribution, but this will arise naturally. And recall, the update equation was that the logarithm of q of mu is the expectation over all the other latent variables, and in our case we only have one more, which is tau, distributed according to q of tau, over the log joint of p of mu, tau, and the data. And of course, recall, when we plug in the data here, we actually mean that that the x vector is fixed to the data. And we can find a similar update equation for the other one, which will be log of q of tau is the expectation over mu over q of mu of the logarithm of the joint of mu and tau and the data, of course. And in order to find the q of mu and the q of tau, we have to find the log joint, and this will be our first task, to find the log joint distribution. So then let's look at the joint and recall once again, since we have access to the directed graphical model, which essentially is what we used to model the data, or that model that we assume for the data, we have access to the joint distribution. And the joint is P of mu, tau, and the data, and it factorizes according to P of tau, because that's a root node, it does not have any dependencies, then P of mu given tau, and then times P of vector x, and then we fix the x vector to the data, so fix x vector to d, and this essentially also reduces the number of variables to just mu and tau, and our random vector of length n will just be fixed. So in this case we have P of mu, tau, and x vector as the data is P of tau times P of mu given tau times, and then we make our IID assumption as always, such that we can take the product over each of the component in a data set. So we have the product from I0 to capital N-1 over P of xi being the xi observation under mu and tau. And of course, we will use the shorthand notation of just P mu and tau for the joint distribution. And then plugging in the distributions that we have. So for the P of tau, we get our gamma distribution, and first the normalization constant of a beta 0 raised to the alpha 0 divided by the gamma function of alpha 0 times tau raised to the alpha 0 minus 1 times e to the minus beta 0 tau. Then we have our distribution over mu given tau, which is first the normalization constant to be tau 0 over 2 pi, then the exponential of minus 1 over 2 times tau 0 times mu minus mu 0 in brackets squared. And again, recall mu 0, that is our fixed hyperparameter, so it is a distribution over mu. And then we multiply with this one here, and this is seen quite often, it's just the likelihood of our data. And if we apply the product to a normal distribution, we get the normalization constant raised to the power of n and a summation in the exponent. So we have a normalization constant of tau over 2 pi, and in brackets we raise this to the power of n, and then we multiply it with the exponential of 1 of tau over 2 times the summation from I0 to capital N-1 over the xi minus mu in brackets squared, and then closing brackets for this exponential term here. Let us ignore all the normalization constants, because similar to when we find analytical posteriors, in this case for the mean field approach, we will then later on also find functional forms, and then we can recover these normalization constants. So it will be easier to derive it without them. So let me ignore these. This is a normalization constant, then 2 pi, and tau 0 is also 1, because it is just a hyperparameter in this sense, but we have it again in the exponential, so we are not losing it. And also the 2 pi here will be a normalization constant. So in total, this will then give us a proportional of tau raised to the alpha 0 minus 1 times e to the minus beta 0 tau, and then tau raised to the 1/2, because it's the square root of tau, then times the exponential of minus 1 over 2 times tau 0 times mu minus mu 0 in brackets squared. And then we have times tau raised to the n over 2, and that is because we have the square root of tau and raise it to the power of n, so we have n times the square root of tau, n over 2 in essence. Then times the exponential of minus tau over 2, then the summation, and here we have the classical differences from the mean. And with this, we found a proportional joint distribution. Recall, if we go back up, we want the log joint. So let us apply the logarithm to it. So we apply the logarithm to what we just found, which will yield the logarithm of P of mu, tau, and the data. And this will be equal up to an additive constant of the application of the logarithm to this. And this term here can be viewed of proportionality in log space, because logarithms of course turn products into sums. So whenever we would use a proportional here, this is equal to just using an additive constant here. And then let's apply the logarithm. And first we get alpha 0 minus 1 times the logarithm of tau. The logarithm applied to this term will just cancel with the e, so we have a minus beta 0 tau. Then here we get plus 1/2 logarithm of tau, and here the exponential again cancels with the logarithm, so we have minus 1/2 tau 0 times mu minus mu 0 in brackets squared, and here we get plus n/2 logarithm of tau, and then the exponential cancel again, so we have a minus tau/2 summation from I0 to capital N minus 1 over xi minus mu in brackets squared. Then let's collect all the terms together that have similar coefficients, and I want to do this in terms of the log tau, and then also in terms of the tau that is just without a logarithm in essence that we can find here. So we get that this one is equal, but it is still equal up to an additive constant towards the log joint. So we have an alpha 0 plus 1/2 plus n/2 minus 1, just move the minus 1 to the last term here, times the logarithm of tau. Then we have minus beta 0 tau. I will leave this alone. I won't join this together with the other taus here. And then we have a minus tau/2. I extracted the minus, the 1/2 and the tau. And then for this term we get tau 0 times mu minus mu 0 in brackets squared. And for this term we would then get plus the summation from I0 to capital N minus 1 over the xi minus the mu in brackets squared, closing brackets. I will denote this one here as xi, and we will do some simplifications, which helps us later on with the derivations, because we want to bring the mu into one quadratic form. Right now here the mu appears squared in 2 terms, and it is extremely helpful if it is only in one squared term. So let us do some simplifications here. The xi is defined as a tau 0 times mu minus mu 0 in brackets squared plus the summation from I0 to capital N minus 1 over xi minus mu in brackets squared. Then first let us apply the rule for sum of squared differences from the mean. So sum of squared differences or distances from the mean. And then we get, first we keep this term here. So this is tau 0 times mu minus mu 0 in brackets squared. Then we get plus the summation from I0 to capital N minus 1 over xi minus x bar in brackets squared plus n times x bar minus mu in brackets squared. And the x bar we have here is just the empirical mean, 1 over n times summation from I0 to capital N minus 1 over the xi, and if you've seen this before, this is nothing else than the maximum likelihood estimate for our mu. And the reason we did this, because we then moved the mu outside of the summation, and it only appears in a regular quadratic form. And here we can then move these two forms together by using the result that we derived in the video on the sum of two quadratic forms. So let us identify the coefficients for this. We have an a here, this will be our y, that's our b, and that's our z. And in this video we derived a c according to an a plus b. So in our case this would be tau 0 plus n. We derived a d according to an ay plus bz over a plus b. And in our case this would be a tau 0 times mu 0 plus n times x bar over tau 0 plus n, and we derived an e, which was an a times b times y minus z in brackets squared over a plus b. Plugging in our values, we get tau 0 n, and then we have mu 0 minus x bar in brackets squared, and then over tau 0 plus n. And this allowed us to move these two together according to the following functional format. So we get an c times mu minus d in brackets squared plus e. And then of course we should not forget about this term with the summation, as this will just keep as an additive constant. So this will be plus the summation from I0 to capital N minus 1 over xi minus the x bar in brackets squared. And then let's plug in the values that we calculated here, and we get accordingly for the c tau 0 plus n, then mu minus tau 0 mu 0 plus n times x bar over tau 0 plus n in brackets squared, then plus the e, which was tau 0 n, and then in brackets mu 0 minus x bar squared over tau 0 plus n, and then plus this term here, which was the summation from I0 to capital N minus 1 over xi minus x bar in brackets squared. And with this, we simplified our xi expression. Let's go back up here and plug this into the xi. So then we get for the logarithm of our joint, so the probability over mu, tau, and the data, this is equal up to an additive constant to alpha 0 plus 1/2 plus n over 2 minus 1 times the logarithm of tau minus beta 0 tau minus tau over 2 times, and then we plug all of this in, which will be tau 0 plus n in brackets times mu minus tau 0 mu 0 plus n times x bar over tau 0 plus n in brackets squared plus tau 0 n, then mu 0 minus x bar in brackets squared over tau 0 plus n, and then lastly the summation term that we have here, and with this one minus x squared, and then closing again, we have an expression for our log joint. It was a long journey so far, but don't let us lose the big picture. We derived this because we now want to apply it to the update rules here in order to identify a functional form for these two surrogate distributions that we have to find. So the next task will be to derive the two surrogates, so derive q of mu and q of tau. And we will start with q of mu. And the update equation was log q of mu is the expectation of tau distributed according to q of tau over the logarithm of our joint, and that is what we just derived. So let us plug it in. This is equal to the expectation over tau according to q of tau, and of course I won't write this down once again, I will just copy it, and that's what we have here. Then let's bring it down and apply some brackets here. And of course we should say that this is equal up to an additive constant because we also have some additive constants here. And we can find more additive constants because if we would apply the expectation, then of course the expectation is a linear operator, so it applies to each of these components here individually. And if we apply the expectation over tau, for instance over this logarithm of tau, then this will be a constant expression with respect to mu, because there is no mu inside. In essence, it does not help us to find the functional form of mu. It will just contribute to a normalizing factor, which we can also just find later on. So we will ignore this and also this one, and consequently also these two, because there is no mu involved. The only place where we have a mu is in here. Of course, don't mix this up with the mu 0, which is just a fixed hyperparameter. I'm talking about the mu, which is this latent variable that we want to find the distribution or the surrogate distribution over. So this will then yield another approximation up to an additive constant over the expectation over tau over, and I would use the shorthand notation expectation tau if it is distributed according to q of tau. And then we are left with this one here, which will be minus tau over 2 times tau 0 plus n times mu minus tau 0 mu 0 plus n times x bar divided by tau 0 plus n in brackets squared. And then by using the linearity of the expectation operator, we can move everything except for the tau outside of the expectation. So we can move all of this in front of it, and then we get minus tau 0 plus n over 2 times mu minus tau 0 mu 0 plus n times x bar over tau 0 plus n in brackets squared. And I will keep this expectation here. So the expectation over tau, or the expectation over tau applied to tau. And then recall what we have here is the logarithm of our q of mu. So we can exponentiate on both sides of this equation. So let's apply this. And then we get that q of mu is, well, and so far we looked at equal signs up to an additive constant in log space. And in non-log space, this means it is proportional. So in this case, this one would be proportional to the exponential of minus tau 0 plus n in brackets times the expectation over tau applied to tau over 2 times mu minus tau 0 mu 0 plus n times x bar over tau 0 plus n in brackets squared, and then closing brackets for this exponential. And I hope you see now where I wanted to head, and we can now identify the functional form of q of mu to be a normal. That's a normal distribution because it has the typical form of it. And the typical form is defined by two parameters. And the first one is this one here, which is the mu of this distribution. And we call this a mu s for mu surrogate. And consequentially, this must be our tau surrogate. And based on this, we can also derive a normalization constant again, which in this case would be just the square root of tau s divided by 2 pi. But we don't have to note this down. I think you know this. So we can just note down that q of mu is a normal distribution over mu with the parameters mu s and tau s inverse in order to mimic the variance. And let us also note down the parameters once again. The mu s is this fraction here. So it is given as tau 0 mu 0 plus an n times x bar divided by a tau 0 plus n. And that's our first finding. And then we have for the tau s, we get that it is a tau 0 plus an n in brackets times the expectation over tau applied to tau. And then this is our second finding. And of course, there is still the open question, what is this here? But we will figure it out shortly. So be patient. Because once we found a distribution over tau, we can then evaluate this quantity if we know the functional form of tau. Well, then let's look at tau. So let's say now q of tau. And of course, recall here in this case, we do a similar approach. The logarithm of q of tau is the expectation over mu according to q of mu. And I will also use the shorthand notation e mu for this over the logarithm of the joint distribution. So the logarithm of mu, tau, and the data. And here I will note it down once again, just for the reference. So we have the expectation over mu, and we have the alpha 0 plus and 1/2 plus n over 2 is just n plus 1 over 2 minus 1 times the logarithm of tau. And then here I will also move the beta 0 tau that you might see, where is it? Here it is, also into this term, and then I have like one big tau term. So I will have to multiply the 1/2 into all of these components here. And this will then give me the following expression, minus opening brackets beta 0 plus 1/2 tau 0 plus n times mu minus, and if we go back up, then we see this one here is nothing else than the mu s that we just found in our distribution on the mu. So I will also note this here. This is nothing else than the mu s we just figured out, plus the tau 0n over 2 times a mu 0 minus x bar in brackets squared over tau 0 plus n. And then lastly, we have 1/2, and then we have the summation term I0 to capital N minus 1 over xi minus x bar in brackets squared, then closing brackets for this one, times tau, and then closing brackets for the expectation. And then we see if we apply the expectation to each of these components here, first, this one doesn't change because the expectation over something that does not contain mu, and we take the expectation over mu, is just whatever we're taking the expectation over. And the same is here in this second component. Aside from this one here where we have a mu, so let me indicate this. So we're taking over mu and we have the mu in here. So in essence, we keep the term that is inside the expectation and we just apply the expectation to this one here. So in essence, this is equal. And also just note that we don't have any constants here anymore because the tau, or respectively logarithm of tau, appears in every of these components here. So finally, we have alpha 0 plus n plus 1 over 2 minus 1 times logarithm of tau minus beta 0 plus 1/2 times tau 0 plus n times the expectation over mu of this one here. And I forgot the square. So this should be a mu minus mu s in brackets squared and then closing brackets for the expectation plus an tau n over 2 times mu 0 minus x bar in brackets squared over tau 0 plus n. And of course, there was this bracket here plus n over 2 times the summation from I0 to capital N minus 1 over xi minus mu in brackets squared and then closing brackets for this one here times tau. And similar to the derivations for the surrogate on mu that we did here, we exponentiated on both sides. And then we found, in this case, we found that it is a normal distribution. Here, if we would do the exponentiation on both sides, we would get tau raised to this here, and you would get an e to the minus this here tau. So in essence, this q over tau is a gamma distribution. So that's a gamma distribution. And the gamma distribution has two parameters, an alpha and a beta. And this one here will be our alpha s, so alpha surrogate. And this one here will be our beta s or beta surrogate. And then let's note this down, that q of tau, so the surrogate over tau, is a gamma over tau under the parameters alpha s and beta s. And alpha s is given as this one here. So it's alpha 0 plus n plus 1 over 2. And beta s, or let us first indicate this as our first finding, beta s will be a little lengthy. It is beta 0 plus 1 over 2 times tau 0 plus n times the expectation over mu of mu minus mu surrogate in brackets squared and closing for the expectation plus tau 0 n over 2, and here we have a mu 0 minus x bar in brackets squared over tau 0 plus n, and then plus 1 over 2 times the summation from I0 to capital N minus 1 over xi minus x bar in brackets squared. And that is our second finding. And with this, we have done the mean field approach for variational inference on our particular problem. And I want to emphasize this once again. If we go all the way back up here, we first made an assumption on the directed graphical model. Then we have latent variables. These are the parameters to our normal. And we want to perform variational inference. We decided for a mean field approach, that is just the product of two independent distributions, for which we derived a general result in an earlier video. Then, based on the directed graphical model, we were able to express a joint distribution, or more precisely, a log joint distribution. And then we were able to derive that the surrogate in mu is a distribution that is given by a normal, and the surrogate in tau is a gamma. But we also said that the surrogate in mu still contains the expectation over the surrogate in tau, and for the surrogate in tau, it's the other way around. So now we have to solve for this. Let us note this down first. I will call this recap, what we've done so far. We've seen that q of mu is a normal distribution over mu under the parameters mu s and tau s inverse. And q of tau is a gamma distribution over tau and alpha s and beta s, the index s for surrogate. And then we've seen that these two quantities, so the tau s and the beta s, still contains the expectation with respect to the other distribution. So this still contains the expectation with respect to the other distribution. But we are lucky because we know the functional form of the other distribution. Then we also know how to evaluate expectations, because for simple distributions like the normal and the gamma distributions, we have analytical or closed form solutions of these expectations. So we will solve this by the analytical forms of the moments. So solve by analytical forms of the moments, because in essence what we had here, like the expectation over tau, was just the first order moment and so on and so forth. Then let's do this. So the expectation over a tau distributed according to our gamma, so distributed according to a gamma over tau under alpha s and beta s over tau is alpha s over beta s. That's what you can look up in textbooks, or you can derive it yourself. But the big point is it is a closed form solution. And similarly, for the expectation over mu distributed according to the normal that we just found over mu s and tau s inverse over mu minus mu s in brackets squared, we see this is nothing else than the second order central moment. And the second order central moment is the variance. And we have our normal parameterized by the precision. The precision is the inverse variance, so this is nothing else than the inverse precision. And with this information, we solved this expectations expressions, and we have full analytical update equations for the parameters of our surrogate posterior. So in total, we have update equations for the 4 parameters. And for handy derivations, we first introduced the x bar, which is the mu MLE, and this one is given as the mean or the average of our data set with the summation from I0 to capital N-1 over xi. And that is the first equation. Then I will leave some space. You will see about this y. Then we have mu s, and we found mu s to be tau 0, mu 0 plus n times x bar over tau 0 plus n. So this is the finding for the mu s. And we can directly evaluate this. There is our hyperparameters involved. We know n, we just evaluated x bar. Then let us first take care of alpha s, so the first parameter of our gamma, and we found this to be alpha 0 plus n plus 1 over 2. So we can also just directly evaluate this. We know alpha 0, it's a hyperparameter, we know n, and the calculations are straightforward. Then we get the second parameter to our surrogate over mu, which is the tau s, and the tau s is tau 0 plus n, and then times the result that we just found out, which is alpha s plus beta s. So it is alpha s divided by beta s, and this will be the result for the tau s. And if we have evaluated alpha s, then we can just evaluate tau s, but we need beta s for it. So let us also note down beta s. And beta s was the lengthy formula that is beta 0 plus 1 over 2 times tau 0 plus n times tau s inverse plus tau 0 n over 2 times mu 0 minus x bar in brackets squared over tau 0 plus n. Then plus 1/2 times the summation from I0 to capital N-1 over xi minus x bar in brackets squared. And then this is our last finding here. And the problem that we face is that the tau s here appears inside beta s, and beta s, or let me use a different color, beta s also appears in tau s. So we have some sort of a circular dependency. So let me note this down. This is a circular dependency between tau s, or the precision of the surrogate normal, and beta s. And of course, whenever we have circular dependencies, that calls for an iterative algorithm. In other words, this algorithm is that we will first evaluate tau s with a guess for beta s, then beta s, and then so on and so forth. And maybe after 100, 200 iterations, we converged, and then we have values for tau s and beta s. You can even prove that this algorithm will converge. I won't do this here, but in a further video, we will find similarities between the variational inference and the expectation maximization algorithm. And then I think it becomes quite clear that this must also converge. There's one more note that I want to emphasize here is that the computation of this one here, so the summation, can be costly, especially if we do this, let's say 100, 200 times, when we have to iteratively update these equations. So it's also meaningful to pre-compute this. And if you pre-compute this, this is nothing else than n times sigma squared MLE. And by this I mean it is nothing else than n times the maximum likelihood estimate for the variance of our data. Because it's like the squared differences from x bar, and x bar is our empirical mean or our empirical mu MLE. So let me also note down sigma squared MLE is 1 over n times the summation from I0 to capital N minus 1 of xi in brackets minus x bar squared, which is what we found here. And if you do this, then this computation here can be avoided and you just use the quantity n times sigma MLE that you calculated before. So let me summarize once again what we did. Going all the way back up here is that we wanted to find a surrogate posterior on our two parameters mu and tau. We knew that we have a true posterior that is analytically findable, so it is actually tractable. Let me also put this that it is tractable, it's not intractable. However, we wanted to do this for an educational purpose because we thought that by our mean field approach, we derived functional forms for our two independent mu and tau. And that is really important. The surrogate is a product of a normal and a gamma, whereas the true posterior is a Gauss-Gamma, which is not the same. And of course, you could also use the surrogate posterior to find a surrogate map estimate. I will call this surrogate map estimate by maximizing the surrogate. So by maximizing the surrogate. And of course, that is actually, compared to our Gauss-Gamma, a simpler task because these two distributions are independent of each other. So you just have to find the mode of the normal or the Gaussian distribution and the mode of the gamma distribution. And you have analytical forms for this. Then we can also, for completion, note this down. I will call this an mu map surrogate. And this one is, of course, mu surrogate. And for the tau, we have to maximize the gamma. And if you were to do this, then you would get alpha s minus 1 over beta s. And you plug in the values that you calculated by the help of these iterative update routines. And then you also have a surrogate map estimate. Thanks for being so patient and staying with me for this long video. If the derivation wasn't clear or if you have any questions left, then please write a comment. I would be happy to answer it. If you enjoyed the video, then please consider liking and subscribing. I would extremely appreciate this. Here you will now see similar videos, and I hope to see you next time, because in the next time we're going to implement this in Python.